To conclude our study of polynomials, I just want to spend some time connecting together expressions, equations, and functions. So in this unit, one of the things we've done is we've learned how to factor higher level polynomial expressions. So for example, this expression we can factor by taking a common factor of x out. Remember, every higher level polynomial expression does not require long division, synthetic division, or the factor theorem. You got to think about what you're given. And then we can factor this down to x plus 3, x minus 2. And the reason that we focus in on factoring in a lot of things is because factoring is the gateway to solving equations. So if I take my expression and I make that into an equation, the expression equal to 0, I know that to solve this equation, I have to first of all factor it. I then know that for these three things to multiply to 0, one of those three things must equal 0. So x must equal 0. X plus 3 must equal 0. In other words, x must be negative 3. Or x minus 2 must equal 0. In other words, x must be equal to 2. And we get the roots of the equation. Now remember that the factor theorem connects with this idea of roots, because remember that if we can identify a root of a polynomial, in other words the value that makes it equal to 0, in other words p of 2 equaling 0, then we know that x minus 2 is a factor. So you see how those connect. We can also think of our polynomial as a function, in other words equaling y. And when we have this equaling y, it means that we can have a whole series of values of x that produce outputs, and so we get a whole graph of points, unlike an equation where only certain values of x can be substituted because we have to get a value of 0. But the connection between the equation and the function is that when the y is 0, that means that the x-intercepts on the function are the roots of the equation. And so if I wanted to graph this function, I can use now a lot of the things that I know about polynomials. First of all, the y-intercept would be 0. If I plus 0 in for x, I get 0. I know that the shape of a positive leading coefficient cubic is like so. And as I just said, the x-intercepts relate to the factors and the roots. So this polynomial function is going to have x-intercepts at 0, negative 3, and 2. And so I can do a sketch of the graph. It's going to start down below in quadrant 3, as we said. I don't know how high it's going to go and where it's going to reach its max. I would have to use the calculator to find that out, or calculus, if you've studied that. And there's a sketch of my shape. Alright, here we have a polynomial equation because I have an equal sign, and it's not a function because I don't have a y involved. So I have a polynomial equation, and since it's a third degree polynomial equation, I know that it has at most 3 real roots. So to solve an equation, we know we set it to 0, as we do with the quadratic equation, and we factor. So we need to factor this polynomial, which in this case is going to require us to use the factor theorem, because if I try to pair it up, it's not going to factor that way. Sometimes that works. In this case, it won't. So I know that my possible a values, which are my roots, my possible roots to this equation are factors of this, plus or minus 1, plus or minus 2. Okay, let's just cheat a little bit by looking at the corresponding function. Y equals this. And I get my cubic shape. And now this looks like there's a value between negative 1 and 2, so I don't know exactly what that is. Let's go over here. It looks like 2 is a 0. Check it out. X equals 2, y equals 0. So I know that if I plug 2 in there, I will get 0. I can see that p of 2 is 0, so I know that x minus 2 is a factor by the factor theorem. Okay, let's use synthetic division to get the quotient, which will provide other factors perhaps. Bring down the 1. 1 times the number in the box is 2. Add 1 times the number in the box, add negative 1 times the number in the box, and I get a remainder of 0. And so my factors are x minus 2, and the quotient would be x squared plus x minus 1. And since we're solving this, it's equal to 0, and we want to solve the equation. Now, this factor doesn't break down any further, and that's fine, it doesn't have to. But remember, we're not done because we're solving the equation. Okay, it's not just an expression, it's what values of x make it equal to 0. Well, we already know 1 because we identified 1 in order to identify a factor. So we know that x equals 2, but there may be values of x that make this 0. And that's a quadratic, which doesn't factor, so I'm going to need to use the quadratic formula. So that's going to be negative b plus or minus square root of b squared minus 4ac all divided by 2a. So x equals, a is 1, b is 1, c is negative 1. Nice numbers. Negative 1 plus or minus 1 squared minus 4 times 1 times negative 1 all over 2 times 1. And so x equals negative 1 plus or minus, that's going to be the square root of 5 divided by 2. And so there's two solutions there, and there's the x equals 2 from above. So I've solved my equation. Okay, let's just do a little check with the calculator here. As a decimal, we get that, 0.618. If we go to our graph, that would relate to the 0 of the function, which looks like the one right in here, 0.618. Alright, and then the other one would be negative 1 minus root 5 over 2. Alright, the next thing we want to do is sketch the polynomial functions below, and this first one is given to me in factored form. 4 different factors, but I have 2 factors of x minus 1. And so I know that when y is 0, my x-intercepts, the zeros of the function would be 0, 3, negative 3 over 2, and this is what we call a double zero because it occurs twice. Now we're going to talk about what that means in a second. Okay. The other thing I can figure out without a calculator is that if I multiplied this whole thing out, if I expanded the binomial squared, that would get a quadratic, times a linear factor of x would give me a cubic, times all that by a linear factor of x would give me a 4th degree, multiplied by a power of x would give me a 5th degree. So this, in expanded form, is y equals a 5th degree power, would be a leading coefficient of 2 if you multiplied all that out. The main thing I'm trying to get from this is that I have a positive leading coefficient and I have a degree 5. I know that my graph starts down in quadrant 3, has 4 hills and valleys, and possibly crosses the x-axis 5 times. Well, I can see 4 times because I got 4 x-intercepts. So the question is, what's going on with this 1? And we saw a little bit about what happens with a double root in the last video. And at 1, you'll notice the graph comes up, just touches, and goes back down. Okay? This double zero, which we call a 0 with multiplicity 2, because the factor occurs twice, the way that shows up on the graph is that the graph around that area at 1 is kind of parabolic. It doesn't cross the x-axis, it goes up, touches it, is just tangent to it, and then goes back down. And that's typical of the way a 0 of multiplicity 2, 4, 6, or 8, anything even works. It comes up, touches, and then goes back down. So this is of multiplicity 2. So in terms of putting all of this together, I have my x-intercept at negative 3.5 at 0, my multiplicity of 2 at 1 and 3, and it's a 5th degree positive leading coefficient, so it starts at the bottom, comes up, here it just goes down and touches, and then it's going to go up like that. Okay, What's not accurate is the minimums and maximums, because for that I would need to use the min-max button on my calculator, and we're not going to worry about right now. The general shape is that. Now we've talked about how a multiplicity where n is even works. Let's look at an example now of where we have a multiplicity of 3, or where n is odd. So if I'm going to graph this function, first of all, I can see that if g of x is 0, I'm going to have zeros, x-intercepts of, set that to 0, 4, and negative 1 will be a 0 of multiplicity 3. The other thing before I look at how a multiplicity 3 works is if I multiplied this entire thing out, I would get a 4th degree polynomial with a negative leading coefficient. And while I'm at it, I can calculate the y-intercept. If x is 0, the constant term at the end will be 4. And so generally I know that my graph, negative leading coefficient power 4, starts down, and it has 3 hills and valleys. Okay, and it has a y-intercept of 4, so I know it's going to cross there. X-intercepts here. The question is, what's it doing at the multiplicity of negative 1? And since we haven't explored this before, let's look at it on the calculator first. An odd multiplicity makes the graph around the point look like a cubic. Y equals x cubed kind of looks like that in this area. The graph comes up to our 0, it levels off, and then crosses to the other side. This is typical of the way a 0 of odd multiplicity behaves. Another variation in question with this topic. Write an equation of lowest degree that has roots -5, 3, and a double root of 1. By roots we mean that when you plug these values in, you get 0. And so by the factor theorem we know that this and this and this are factors. This is a double root, or multiplicity 2. And so putting all this together, I'm talking about x plus 1 squared, 2 factors of that, multiplied by the other 2 factors. And I want an equation, which means I want it equal to 0. There we go. Let's take a look at the corresponding function. So I have an equation that has roots, or corresponding x-intercepts, as indicated. Now the other thing I could do is I could use this as an equation. Because if I set my factors to 0, the 1/2 isn't going to give me any additional zeros. What it's going to do, though, is it's going to vertically stretch the graph. You'll notice that the graphs have the same roots, zeros. The other points are different, but it's the roots that we need to have be specific values. All right? So you can actually, given these factors, multiply that by any non-zero value, and your equation will still give you the indicated roots. But now let's just take a very similar question where we're asked to write a polynomial function of lowest degree that passes through this point and has the same zeros as above. So the difference here is, first of all, we're looking for a function, f of x, whereas up here we were just thinking about this in terms of the graph. It has the same factors, and the question is, can I multiply this by any non-zero value? No, I can't. It has to be a certain non-zero value, because the difference here is that this graph must pass through this point, 1, 4. So to make it do that, of course, we're going to make y 4 when x is 1. So let's plug those values in. And I multiply these together, I get negative 48k equals 4. And so therefore my function, plugging this back into here, okay, let's check this out on the calculator and make sure that the graph passes through the point 1, 4. Trace when x is 1, y indeed is 4.